Good evening. We'll start in a few minutes. Since today is the first session, people might have difficulty finding the link and joining. So we'll just give it a few minutes. In the meantime, people who joined, hope you can hear me and see my screen clearly. If not, please drop a message on chat. Thank you so much. Let's wait a couple more minutes. Okay, let's get started. Hopefully, everyone has joined by now. So, welcome to the week 1 live session for the GPU Architectures and Programming course. So, I'm Prashanti. I'm a PhD candidate at IISc and a Prime Minister's Research Fellow. So, I'm the TA who will be conducting these live sessions for this course. So, let's get started. So today, since this is the first live session, I'm not sure how many of you have taken an NPTEL course before, how many of you are aware of these live sessions. So we'll set expectations on what these live sessions are for and what you can expect from here. And after that, we'll move on to some technical content. Yeah. So you will be having 1 2 hour live session conducted every week. So this is the first week, and you will have 13 of these, right? 12 for 1 week of course content from NPTEL, and the final session will be a revision session which kind of covers all your doubts and questions. The typical time for this is Sunday 6 to 8 p.m. Like today, there is no other time. In case there are any last minute reschedules, mainly because maybe I'm traveling to a conference or something like that, you will get an email very much ahead of time from NPTEL. So just watch out for that. But this might happen once in the 12 weeks, not more than that. So all other sessions will be at the regular time, Sunday 6 to 8 p.m. So next, moving on to what you can expect from these sessions. So these are sessions that will be focused on problem solving. So these are meant to help you with your assignments that are posted weekly and your final exam of the course as well. So every week's session will be aligned to that week's course content. For instance, this week is the week 1 live session. So we will align it to the week 1 course content from NPTEL. That's how I kind of do it. So what we will have is some problems that are similar to your assignment questions, but we will not be discussing exactly the same questions, because again, you're meant to solve that on your own and submit it. What we can do is, once you've submitted it, once the deadline of that assignment has passed, and maybe once the solutions are released, if you're still not clear about something and you want clarifications on that, you can always ask me, and then I can take up those questions and explain them to you. But typically, we will solve some questions that are very similar to your assignment questions and any doubts that you have from that week's course lectures or slides, right? And since there are a lot of people joining, today I see around 20 people, so we will limit interaction to the chat box, right? Because multiple people unmuting in the middle or accidentally leaving their audio on is very distracting to everybody else. So we will have all interactions through the chat box. So feel free to post doubts or questions anytime, right? I may be in the middle of explaining something, but that doesn't matter. Please post your questions or doubts as and when you get them. And I will maybe finish explaining something and get to your question in 1 or 2 minutes. So that's fine. But the primary point of these sessions is to have interaction, because your lectures are pre-recorded, your assignments, you kind of do it on your own and submit. Solutions are also released offline, right? So the primary intent of these sessions is to give you some interaction with a person who can address some of your doubts and questions so that you can do better in the course. So please use that opportunity very well, and the more you ask questions, the more you interact with me, I will kind of know what background you're coming from, what you need more help understanding, and I can help tailor the sessions accordingly, right? And in case you have internet issues or something during the session and you drop off, don't worry, you can always join back, and all of these are fully recorded. So the 2 hours recording will be posted on YouTube, and the sheet will be shared with you by NPTEL. Maybe in a week or so, you will get access to that sheet. So thereafter, you can look at the recordings on YouTube. The slides will also be shared with you, right? So anything that I'm using as material in this session, you will definitely get access to it after the session. So in case you have internet issues and drop off and join in, all that is completely fine. But definitely try and attend these sessions rather than just watching it on YouTube, right? Watching it on YouTube will help you, but you will not get the benefit of interaction. So it's again going to be like watching your lectures. You will get to watch it and you learn something from it, but you will not get to clear your doubts in an interactive manner. we have a question. Can these sessions be accessed again? Yes, for sure. So, like I said, you will get links to the recordings which are on YouTube, and they will be on YouTube forever. So, you can definitely look at the recordings. Slides will also be available in a drive folder which you can access whenever you want throughout the duration of the course. Voice is breaking a bit. Thanks for bringing that up. Is that for everyone else? If so, I'll try and switch my networks. If it's just for one person, then it's probably your network. Can someone else confirm if you can hear me clearly? Okay, I kind of changed networks and joined. Do you still have an issue with my voice? Okay, it's better. Great. So, in case you have an issue with my voice, please let me know immediately. Glad to hear that it's fine now. So, we'll continue. And for people who just joined, we are just going through some logistics of the live session. Please try to join on time from the next time. Since this is the first week, I understand you might have some issues. That's okay. But please join at 6 o'clock from next week. I see there are people still joining. Okay, so this is pretty much it about the live session. So let's move ahead. So how we are going to structure these 2 hours, right? So this is also something I'll talk to you about. So the first 30 minutes we will spend doing a quick recap of that course, that week's course content. For instance, today is week 1. So I will briefly go over some of the concepts that were covered in your week 1 lectures. And feel free to ask your doubts or questions then, right? And after this, we will take 1 hour to solve some problems. So some of these might be numericals. All of these typically will be multiple choice questions, but some of these may be numericals, some of them may be just things that are subjective or things that are based on recall. But I will give you time to solve accordingly, right? Maybe a minute, maybe 2 or 3 minutes also if needed. So this is so that you can solve it right then and answer on chat. So don't hesitate if you kind of solve it and have an answer and you're not sure if it's correct. That's okay. Please post your response on chat. For instance, if the majority of you are confused and are getting a particular wrong option, then I will take more time to explain why that is the wrong answer, and that will help you. So please make sure to post your responses on chat, because without that I have no idea what you're thinking, and I will explain the solution for sure, but your confusions and doubts may not be addressed. And apart from this 1.5 hours, we have 30 minutes for doubts and questions, right? So we will go through, for instance, questions that are posted on the discussion forum. So the regular TAs monitor this Google group, which some of you may be aware of, others may not. I'll briefly tell you about this as well. But any questions that are posted here, I will also once go through it in the live session. And since this is a 2-hour session, it might be it might get a bit long. We'll take a 5-minute break midway. So since it's 6 to 8, around 7 or 7:05, I'll kind of let you know that we'll pause for 5 minutes and come back. So feel free to use this to just walk around a bit or get water or whatever you need to do. So this is how we are kind of structuring the live sessions. And again, interaction is the most important part. So please feel free to ask questions or bring up doubts and things like that. And if you would like something more, so today for instance, we will go through the live session in this format. If you feel that maybe I haven't understood week 1's lecture content at all, I would like to have more of recap, maybe 45 minutes of recap. At the end of the session, when we are 5 minutes to closing, I will ask you if you have any feedback. Feel free to let me know that I would like a more detailed recap. Or if you feel that the problem solving is helpful, you would like more of that, feel free to say that as well. Or if you're happy with the structure, that's also fine, but letting me know will help me change it accordingly. So yeah, this, in case you guys didn't know, there is a discussion forum there. So if you on the course tab, I think it's visible under ask a question or something like that. So you can use, this is a Google group. Since you'll get access to these slides, you can also click on this link that's there, and you can ask questions here and the TAs will monitor and get back to you. I can see that some of you have already asked a question, so that's good, you're aware of it. For those of you who are not aware, use this also to ask questions during the week apart from the live sessions. Okay, so what do you need to do for each week's live session, right? So to make the best use of this, this is what I recommend. So for instance, if you're coming to the week 1 live session, please watch that week's lectures on NPTEL, right? Because they are released, I think, a week ahead of time. So for instance, today, I think the week 2's course content has already been released. So please use this week that you get in between the release of the lectures to the live session to catch up with the lectures. If you come here without having watched any of the lecture videos, most of the things that I tell you or the problems that we are trying to solve will probably go over your head unless you're already familiar with the course content, right? So to make the best use of this session, it would be very helpful if you watch the lectures ahead of time. That way you'll kind of be aware of what things you're not understanding well. You can ask those as doubts. You can also try to solve problems based on that week's course content. Because remember, we are not going to do a detailed recap of whatever was already done in the videos. Because the video content itself is around 2 hours. So I definitely cannot spend another 2 hours explaining that. So we will just be doing a quick recap of the video content. So if you definitely need to watch the lectures before coming to the live session in order to understand what we are talking about. Also try to solve the assignment that is released so that you will get an idea of what problems you particularly find difficult, and we can focus on those during these sessions. If there are references or links from that week's course content, again go through them. They may not be very relevant to your assignment, but they'll definitely help you understand more about the material. And since this is a slightly advanced course, this will kind of help you go beyond what is strictly there in your course material. So with this, I think we are done with the logistics. So first of all, any questions on any of this? Do you have any doubts or do you want clarifications on something? Please ask now. We'll take a little bit time today on this because I won't repeat this again in the other live sessions. So please ask if you have any questions on the live sessions itself. Anything that's not clear. I'll wait for a minute. If you have any questions, please let me know. Book for solving assignments. I think there are reference textbooks given, but I don't think they have assignment questions there. So I would suggest mostly sticking to the assignments that you get and the live sessions, right? That should mostly cover most questions that you'll get in your exam. I don't think there is a textbook as such that will help you solve assignments better. There may be textbooks that help you understand the topics better, and those are already given in your references. Hope that helps. Okay, will there be some labs or will all the assignments be MCQs? I think typically there is 1 or 2 programming assignments, so you can expect one slightly before midway, right, before week 6, right, once you get well into the GPU architectures part, and once towards the end. So there might be a maximum of 2 programming assignments. Other than that, most things will be MCQs. Any other questions? I'll wait for a few more seconds. If you have questions, please feel free to post. Okay, if there are no questions, let's move ahead. So let's do a quick round of introduction since there are not too many people, there's just 20 to 25 people. So please introduce yourself on chat. This is mainly so that I understand what background you're coming from, and again, that will help me tailor the content of these live sessions. For instance, if most of you are from an undergrad background, then I'll do it accordingly, and so on. So that's about it. I'm not trying to gain any other information about you. So, one question: will there be any tests in the live sessions? Absolutely not. So, this is not any form of a test or an evaluation or something that you'll be judged upon. It is intended purely to help you understand the course material better and to solve assignments and exams. Right? That's it. Nothing else. So you can follow this template, your name, what you do, for instance, student in some college, and what background you are from. For instance, I'm from undergraduate student in computer science. And what is your intention behind taking this course? What are you expecting to learn? Maybe I'll go first. So, my name is Prashanti. I'm a PhD candidate at the Indian Institute of Science. I broadly work in computer systems but with a closer focus towards hardware. And I am teaching this course again because my research involves some amount of GPU architecture knowledge, and I'm generally passionate about systems subjects. So, who wants to go next? Don't hesitate. Like I said, there's nothing else about this. It's just a way for you, all of you, also to know what the rest of you are doing. Hi Shri, research scholar. Okay, hi Aditya, third year CSC, parallel programming stuff. Nice. Faculty in engineering college. Nice to meet you. Working in AMD. Nice. Undergraduate in CSE, GPU programming. Nice. Anyone else? Hi Arjun, nice to meet you. VLSI and FPGAs, okay. Software engineer, okay. Offloading program from CPU to GPU, okay. Masters in VLSI, nice. Graphics programming and Compark. Game development, okay. It's different. GPUs and compilers, okay. Nice to meet you, Pratiksha. MCA, okay, nice. Anyone else? We'll wait for a minute more. Nice to meet you. Anybody else? I think most of you have introduced yourselves. undergraduate in CS. Nice. Anyone else? Yeah, that's fine. If you've already introduced yourself, that's totally okay. Just waiting in case anyone else is typing. Yeah. Okay, so I see a good bunch of undergraduates and again, then people from very different backgrounds also. So I'll try to go over things from first principles, but don't hesitate to ask, right? If you don't understand anything, no matter how basic it seems, feel free to ask because again, everybody here is from a different background. So it's perfectly fine if you don't understand something that seems obvious to everybody else, feel free to ask. That's why I'm here and I'll make my best effort to explain it to you. And if I'm not able to explain it well enough in the same session, I'll definitely try again in the next session, right? So feel free to ask any questions on whatever it is. So yeah, let's move on from the introductions to a few other logistics about the course, right? So this is again mentioned in your course webpage also, but just to reiterate, so some topics that are overlapping with computer architecture you will find in the classic Hennessy and Patterson book. Apart from that, there are a couple of other books that are also recommended. These two, this one will help you understand OpenCL, which comes in the later part of the course, and this one will help you understand some of the programming aspects of it. But typically the course lectures themselves are fairly they go into a lot of detail, right? So you can watch those first and then use some of this additional material to uh, to kind of clarify things that you don't understand very well. And sometimes your slides itself will have references on individual topics, and in my live sessions also for topics that typically people have trouble understanding. So I've TA'd the same course last year as well. So I typically put in content or references from external sources as well, and I link them in the slides. So you can go through those also, and if you still don't understand something, feel free to ask me. Okay, so here's how the overall syllabus of the course looks like. So week 1 is just your traditional computer architecture, right? RISC versus CISC, pipelining, the memory hierarchy, and then SIMD. And then from week 2, we go on into GPU architectures, CUDA programming, some amount of details on synchronization, scheduling, and memory accesses, and then we look at a few optimization examples, and then we move on to OpenCL. So majority of this would be in CUDA, and then the last parts are in OpenCL, and finally we look at an application which is to neural network training and inferencing. And again, most of you who would have used GPUs in today's context typically would be either for gaming or for some deep learning stuff, right? Typically training or inference. So we have a question. Are there any projects or case studies? As far as I know, not really. You might have assignments that are hands-on, but again, they will be kind of a programming assignment based on some of these concepts. They're not really like a project or something that is an end-to-end application. You can of course choose to do something like that on your own and use the concepts that are taught in the course. But officially, no. As far as I know, there are no projects or case studies for this course. Deep learning knowledge, not really. It would help if you had some, but it's okay if you don't, right? It's just a couple of weeks, so you can, and things will again be explained from the basics of first principles, so you don't really need to know. Computer architecture or organization, if you're familiar with it a little bit, some of these things will be easier, but the other things I think are the other things like deep learning are not really necessary. topics for project implementation, again, since this is a systems course, right, where you're looking at GPU architectures and programming, most people would end up using this knowledge in an application project where you could be doing deep learning training or inferencing, and you may be looking at some optimizations you want to do there, right? So you might use it in that context, or if you're doing direct CUDA programming, again, this will teach you some levels of optimization. But beyond that, I don't have any project ideas that I can hand out to you. These are two directions that you can explore, right? Optimization in various contexts. How do you optimize a particular application? For example, neural network training, using some of the knowledge that you have about GPU architecture. Again, that's not very easy because there are a lot of tool chains that do this, right? For instance, your compilers and even your frameworks today, PyTorch, TensorRT, all of these do a lot of these, kernel fusion, thread block fusion, etc. So it's going to be more of a demonstration rather than a real improvement over these things. But you could also do something that uses some of these principles in an end application. So maybe you should look at some project ideas and then maybe ask me if you have specific questions on one or two of them. But beyond this, I don't have any ideas at the moment, and this is not an official part of the course, so I don't want to spend too much time talking about project ideas. Okay, any other questions before we move forward? Okay, if not, let's continue. So now we've covered all the logistics of the live session and of the course itself. So we'll get started with the week 1 content that's actually part of the live session. So as if you've seen the videos, you would have realized that this week is about basic computer architecture. So we look at things like pipelining, the memory hierarchy, CISC versus RISC, and then data path, some hazards, the notion of locality, cache mapping, cache replacement, instruction level parallelism, branch prediction, and register renaming. Again, it's a very quick overview of computer architecture. So today what I will do, like I said, I'll use 30 minutes to give you a quick recap of some of these topics. But what you definitely should do if you don't understand something very well, for instance, if you don't understand ILP, please leave a message in chat anytime you want, right, during today's session. And then in the next live session, I'll definitely go over some of those slides in detail, spend maybe 5 to 10 minutes explaining that. So this week, whatever lectures you watched and whatever slides you've gone through, based on that, if you have any doubts or questions, please ask in chat. And if you have doubts, I think there was a prerequisite assignment sort of thing, week 0 assignment. So for that also, if you have doubts on anything, please feel free to ask. We can discuss those questions in the next week's live sessions. But for today, we will move on to some recap, right? So this is the pipelining in context of pipelining. People are still joining. 1 second. Okay. So in the context of pipelining, we look at a typical 5-stage pipeline, right? So you have fetch, decode, execute, memory, and write back. So in fetch, you're kind of loading the instruction, and then in the decode stage, you're understanding what the instruction means, and then depending on the type of the instruction, whether it's an arithmetic or logical operation or a branch computation, you execute it. And then you could have a memory stage where you read or write data from or to memory. Typically, these are load store instructions. And then you do a write back where you update the register file. So this is the basic 5 stages of execution that you have. Now, the idea of pipelining is that you operate these 5 stages in parallel for a sequence of instructions. So every stage is always processing some instruction or the other. So if you look at the fetch stage, it may be processing a certain instruction, the decode stage will also be processing a certain instruction, right? So we look at a detailed example in the context of the assignment problem. So here I won't go into too much detail, but I typically get a lot of questions on pipelining. So I will cover that in detail in today's session. So typically in every clock cycle, one instruction completes. This is the ideal scenario. But due to some issues that were discussed in the course as well, like pipeline hazards, this may not really happen, right? That's about pipelining. A similar thing on the memory and the storage side. So the memory was probably covered in this course. So you have CPU, then you have cache memory, primary memory, and secondary memory, right? And again, if this is a typical figure that you have in one of your, so you have a question. What is? Could you complete that sentence, please? Write back, is it updating on software or registers? No, it updates the register file itself, not any software. So this, all of this we are talking at an architecture level, right? So we are talking about the registers and the program counter and things like that. What is the register file? So 1 second, let me see if I can also share a reference on this. So this register file typically refers to the set of processor registers that you have for a CPU, right? So you may have 10, you may have 20 or something like that, and this is something that's part of the architecture of the CPU, right? Depending on how many registers you have, and this is kind of visible to you, and in the write back stage this is updated. Hopefully that helps. So I think going through a quick recap of computer architecture might help all of you, especially those who haven't had a Comp R course formally. I'll see if apart from this I can share. So what you should do is look up computer organization or architecture recap, right? So typically in a lot of master's courses, you will find a prerequisite sort of lecture slides where people talk to you about what are these basic notions that are used. If you go through one of those slide decks in addition to this course lectures, it will probably help you. I'm just looking quickly for something like that. If I don't find it in under a minute, I'll probably share it in the next session. But going through something like that will definitely help you understand what are, for instance, what is a register file or what does the write back stage do, right? Yeah, I think I'm finding very detailed summaries of the computer architecture textbook, but should definitely find a very quick recap. Okay, let me look for that in the break. Since we're already at 40 minutes, it would help if we kind of made some progress and then came back to this. But if you don't understand some of these terminologies, it's definitely because you've not had a computer architecture course before. So looking at a quick recap of that will definitely help you understand this better. Okay, so moving back to the memory and storage hierarchy. So again, this diagram probably illustrates this in more detail and along multiple axes. That's why I picked this. So if you start at the top, the registers, right, you'll see that they are smaller. That's indicated by the size of the rectangle or the cuboid, and this grows larger as you progress below. So if you notice, you'll see that your hard disk is, these days it's probably 1 terabyte or at least 500 GB, right? Tapes are again a very old form of secondary storage. But when you compare that to your main memory is basically your RAM, which typically on your laptops is maybe 16 GB or 32 GB, maybe even 64 GB, right? So you see the size dimension of this, right? This is something to keep in mind. So one axis is the storage capacity or the size. The other axis, of course, is the access time itself. So registers are a lot faster, caches are a little slower. So as you go down this axis, things get slower, right? So main memory is again slower than cache, and then your secondary storage is much slower. So, and you also have a separation of volatile and non-volatile, and the newer technologies like non-volatile memory blur some of those. But this notion of multiple axes is something that is very useful to keep in mind, right? So it's not just that something is faster, but there is also a size dimension that comes into play. You might wonder why can't I have maybe thousands of registers, right? So there come into play other dimensions. For instance, the cost it takes to put that many registers on the chip, or it could simply be the space that's available on the chip, right? So all of these dimensions come into play, and each of these have very different technologies underneath. So this is something to keep in mind. And I will have some of these prompts. It's okay if you are not able to answer some of these immediately, but think about these, right? So what is the memory hierarchy or the memory equivalent on the GPU? So are there registers? Is there cache memory? Does it have its own primary memory? These are some things to think about. They will be addressed in later parts of the course. But if you know about GPUs and you've already used them, this is something to ask yourself. So think about this. So we have a question or a comment. We use some registers, and in those, some of them are software and hardware registers. Most of the software registers are updated by the kernel mode drivers to change graphics power states or wake up graphics or load virtual addresses. Okay, this is a bit more complicated than what I understood from your initial question. Let me think about that. I see. So you're asking about software and hardware registers. In this context, right, in the GPU context, as in some of them are used to change power states and things like that. I'm not very sure about this. I can, of course, look it up and get back to you. But in the context of computer architecture and the basic stuff that we are talking about, I don't think some of these things are very important. But that's something very interesting. I will definitely look that up and let you know. Yeah, that's the typical answer that you get from basic computer architecture, right? Your usual registers. But what you're asking is something a little more sophisticated that I need to think about and also look up. So I'll do that and get back to you maybe in the next week's live session. But that's an interesting question. Okay, let's keep moving ahead. Okay, so then we briefly touch upon the idea of locality. Again, locality is used in various spaces in terms of caching, right? So here, when we talk about cache, we could be talking about the architectural caches, which are typically very small. You also have caching that happens at the OS level. So if you've taken an OS course, you might have heard of the page cache, where the DRAM or the main memory is itself used by the OS to cache some stuff. So even then, the same ideas play a role. So this is something that's good to know in general. So the idea of temporal locality is if something is referenced, it will typically be referenced again soon. The idea of, so basically the dimension we're talking about here is time. So locality in time, right? And here we are talking about locality in terms of space. So if an item is referenced, items at nearby addresses will be referenced soon. So a typical example that you would think of in this context is probably an array read, right? If you're sequentially reading an array, then you kind of move from one element to the other, and things that are at close by addresses are going to be referenced next. So what is the advantage of knowing things like these? You could use them to make some caching decisions. For instance, if you know that things that are adjacent or at nearby addresses are going to be referenced soon, you could bring them into the cache ahead of time. And you could also make eviction decisions, as in what do you want to remove from the cache based on these ideas. So that's the idea of locality. Hierarchically organized, we already saw that. Registers are the fastest, and like I said, all of these levels use very different technologies underneath, right? So the cache memory uses SRAM, static RAM basically, and main memory uses DRAM. Again, some of the factors like cost and speed come into play in these different technologies. So cache uses SRAM and main memory uses DRAM. Okay, so today I think I've kept the recap a little shorter because we have around 1 hour of questions to go through, and the introduction also took a long time, right? So let's move on to the next part, which is the discussion forum questions. So I think there was just one question, so I put that here. So this was about question 4 in the assignment 0. So the answer key mentions that the correct option is option C, int star n ampersand aij. But the person asking the question says that option C means that we are using size of int star for malloc, when we should have actually used size of int to allocate memory for the row of the matrix. Therefore, the correct option should be int n ampersand ai. And the answer given was this is a valid reason, and the actual answer will be int n and ampersand aij, although this is not there in any of the options. So please note this about the assignment 0. So this is the correct answer. If you've not seen this before and are seeing it for the first time, please go through question 4 again, and if this is not clear, please ask me. So this was a basic, I think, C programming question, so I have not really gone into detail here. But if you don't understand, not just this question, right, anything in the assignment 0, please post a message on chat even right now, right? I'll definitely answer your question in the next live session. So anything from assignment 0 as well as week 1, if you did not understand a particular topic, you can post it on chat. I'll wait a minute before we move into the problem solving session. If you have any doubts or questions, please ask them. Cycle time and latency, yes, that's part of the questions today, so it will definitely get answered in today's questions itself. Any other questions? Okay, that's an interesting one. Why do branch predictors work like they do? As in, why go by statistics? Okay, so what is an alternate method that you think would be good to do branch prediction? I think using statistics is kind of the intuitive or the obvious method, right? So you have access to historical data. So you'll notice this in a lot of OS and typically a lot of system subjects. So whenever the system or the hardware or the software has some data that's available on previous uses. For instance, in this case, the branch history, what branch was taken, right? It tries to use that to its benefit to do a better job of prediction. So if you had no knowledge, maybe what would you do? Half the time you'd predict true, half the time you'd predict false, or maybe you could even predict true all the time, right? But given that you have some knowledge of the branch history, then why not use that to make prediction decisions? So that's, I think, the intuitive and obvious answer for why branch predictors use statistics. But I'm interested to know, did you have any other ideas on how you should do branch prediction? Because there could be. So if you do, feel free to share that with us. Okay, so if not, maybe I can help you understand a little better even with this caching example, right? So when we have a limited cache size available, we have to make decisions about what to keep in the cache or what to remove from the cache, right? So if you had some knowledge of what is going to be referenced next, right? Or if you could make a guess, an intelligent guess on that based on some notions like this, let's say temporal locality or spatial locality, right? It would help you get a better cache hit rate. So if you didn't know at all, if you had no idea on what the previous caching pattern was, or you couldn't use any principles like these, then you would typically make very bad guesses on what to cache or what to evict, right? So this gives you some information on how to make an intelligent decision to cache something or evict something. So similarly for branch prediction. Hope that helps. Okay, I'll wait another minute to see if there are any other questions. Sure, glad to know that. And some of these are also research directions that a lot of people are working on, right? So people might have tried out very different approaches. Again, you might see some of those approaches reported in a textbook, the most popular ones that are typically used, but some more you might not see, you might see them in very obscure research papers. So if you have an idea, there's no harm in kind of using this forum to discuss about it. This applies generally to everybody and your questions. Okay, so I think we are any other doubts or questions? Now is a good time to ask. I'll make a note of it. Even if I don't have time today, I'll get to it next week. Okay, if not, what we'll do is what is the difference between core and a thread, right? So okay, that's a good question. So some of these notions are at the intersection of hardware and software, right? So you have to keep in mind at what level the abstraction is. Maybe that's a slide I will also show you next time. But broadly, core is used to refer to hardware, right? So when you hear about like a CPU with 8 core CPU, right? It refers to the hardware part of it. Now thread is typically used in the software context of it, although with notions like hyperthreading. If you've heard of hyperthreading, it is to use some form of redundancy in resources. So if certain amount of resources are idle, you could actually have parallelism, as in two threads running on the same hardware unit or the same core, right? But other than that, thread is typically used in the context of processes and threads, right? The abstraction level here is a software notion. So I think I have a nice slide on some of these terminologies and what level of abstraction they are at. So I'll bring that up in the next week, and that will probably help you understand this a little more better. But for today, here's the short answer. Okay, since we are at okay, need more clarity on cache parameters like cache hit, miss penalty. We can have that in the next week, but I'm just thinking from the overall point of view of the course, since this goes a lot more into GPU architectures than compact, it might not be very relevant. But I can definitely have maybe 5 minutes worth of content on it, which will help you understand the basic idea of caching and hits and misses and things like that. Okay, so since we are almost at 7, what we'll do is this is a clean point to take a break, a logical break, before we get into the problem solving. So we have around 10 problems to solve once we come back from the break. And at 5 minutes a problem, I think we should be done well before 8 o'clock. So we'll take a 5-minute break now. So it's almost 6:57. So we'll resume at 7:02. I'll keep the call running, but feel free to step away and then come back at 7:02. See you in 5 minutes. Okay, let's continue. So we have a question. Do we get recordings of this class? Yes, you will. I mentioned it earlier, but maybe you were not there. So you will, all of these are uploaded to YouTube within a day of the session, and you will get access to a sheet from NPTEL from where you can get the YouTube link. So yes, you will get recordings of the class. Any other questions before we get started? Okay, if not, let's get started. So, like I said, we'll keep this problem solving part very interactive. So, I expect you guys to, I will give you time to solve questions, but please post your answers on chat once you get them, right? Doesn't matter if it's right or wrong, it's not an exam, you're not going to be evaluated. It's just so that I get an idea of what you guys are thinking is the right answer, and I'll help clarify if that's right or wrong. So, let's start. So this is the first question, and this data will be common to questions 1, 2 and 3. Consider a computer system with 32-bit memory addresses, 2K byte cache organized in a direct mapped manner with 32 bytes per cache block. Assume that the size of each memory word is 1 byte. Calculate the number of bits in the word field of the memory address. And your options are 5, 6, 7, none of the above. So since it's a numerical, I will give you 2 to 3 minutes to solve it. Please post on chat once you think you have the answer. Okay, we have an answer. A, 5 bits. Anybody else? Take your time if you're still solving it. I will give you 2 minutes. Five bits. Okay. 5 bits. Okay, 5. Anyone else who thinks something else is the answer? Don't know. Okay, that's fine. We will discuss a solution. So after each question, if you don't know the answer, I will discuss the detailed solution and how to get it. Pay attention to the explanation and then ask me if you don't understand. Okay, I think that's enough time to solve it. Anyone needs more time, let me know. Otherwise, we'll discuss the answer. Okay, I'm guessing everyone has solved it by now. So the answer is 5, but let's discuss how to get the 5, right? So for all these cache questions, there are typically 3 fields, right? And the first one is tag. The second one, you'll see it being referred to in 2 different ways, but they mean the same. You'll see terminology saying cache line or terminology saying cache block. And the third one will say the word or the offset, right? So for instance, this question asked about how many bits the word field has. So before we go there, what do these 3 fields mean, right? So the word or offset tells you which word or byte in the cache block the data that you're looking for is in, right? Because the cache block itself has a number of bytes. So this is kind of the offset in that cache block where exactly is the data that you are looking for. Then there is the block field or the line field, which tells you which cache block, right? Because again, there are multiple cache blocks that you're dealing with. And finally, the tag, which tells you which main memory block this is referring to. And again, you can have scenarios where multiple main memory blocks map to the same cache block. So these are the three fields that are there, and this will be useful in general to solve all cache questions. So now coming back to this question, which asks you about getting the size of the word field, right? So here the block size was given to us as 32 bytes, which is 2 power 5 bytes or 2 power 5 words. So given that your each cache block has 32 bytes or 2 power 5 bytes, how many bits do you need to figure out where in the block the particular thing you're looking for is in, right? So you need 5 bits, that's all. So that's why the answer is 5. So for this, you'll directly need to use the block size, look at what power of 2 it is, and you will need that many bits to represent an offset in the block. So if you had 5 bits, you could traverse all of these 32 bytes in terms of offset. So hopefully this is clear now. Now for people who said they didn't understand or don't know, please take a look at this again and let me know if you have any further questions after this explanation. Because if you don't, for instance, understand if you still don't understand this, then it may be worth spending some more time on cache mapping in the next session. So don't hesitate. If you still don't understand anything about this, let me know. Understood? Okay, good. Okay, I will move on in the interest of time. If there are any other questions, feel free to ask. Okay, voice is... Oof. Okay. Is it any better now? If not, I'll just change networks. Better. Okay, great. That's good. Okay, never mind. Yeah, let's move ahead. So the next question again will have the same data as question 1. Calculate the number of bits in the block field of the memory address. Again, your options are 5, 6, 7, none of the above. Okay, we already have one answer saying 6 bits. I'll give you 2 minutes. So for people who have not noted down things from the first question, I'll just go back here, and you're now asked about the block field, how many bits it takes. We have one more answer saying 6 bits. Anyone else? 6 bits, okay. Six, okay. Wait for a few more seconds. For the first question explanation, we have 32 bytes per cache block, which maps to the word field. Yes, so we are talking about the cache block size. Yes, that is 32 bytes. And yes, this maps to the word or the offset field. So remember, try to logically understand this rather than blindly using, I feel that's more helpful in understanding it. So this tells you about which word or byte in the block the data is in. So for this, you directly have to use the 32 bytes part. Okay, 11 minus 5 equal to 6. I'm guessing you're talking about the next question. Okay, I'll wait for a few more seconds and then we'll go to the next one. Okay, let's take a look at the answer. It is 6, like all of you I think guessed correctly. So we'll take a look at how it is 6. So your cache size here was 2 kilobytes, which comes to 2 to the power of 11, right? Yeah, and after that you need to get the number of cache blocks, because remember here you're trying to, in this field, in the block field, you're trying to figure out which cache block. So to know how many bits you need for that, you basically need to know how many cache blocks there are, right? So to find out that, you have to take the total cache size, which is 2 power 11, divided by the block size. So the block size you got earlier as 2 power 5. So that gives you 2 power 6 as the number of cache blocks. So in order to represent this, how many bits do you need in the block field? You need 6 bits. So I think that was what 11 minus 5 was referring to, this 2 power 11 divided by 2 power 5. But this is how you get the number of bits. So see if this makes sense, and if you have any follow-up questions. I'll wait for a few seconds before moving to the next one. Okay, if no further questions, let's move to the next one. Again, same data. Calculate the number of bits in the tag field of the memory address. Okay, 21 bits. 21. Anybody else? 21. 21. Wait for a few more seconds. I think this one is more straightforward, so less calculation. Okay, I think everyone has replied. I'll wait for a few more seconds in case anyone is calculating. Okay, if not, are these concepts taught in week 1 lectures? I think broadly the idea of caching was covered, but I don't particularly recall if direct mapping and bits in each field were taught, right? But since computer architecture is weekly expected as a prerequisite to this course, you might be asked some of these questions even if they are not directly demonstrated in the lectures. For the rest of the weeks, I don't think that would be the case. Most, if not all, questions will be directly covered in the lectures. But this one, since it's a recap, you might find things that are not really there in the lectures fully. I don't really remember particularly about the cache mapping though. Maybe someone else who's watched the lectures recently can tell me. Was there something about cache mapping? There isn't. Okay. Okay, in that case, if people have doubts on cache mapping or you want more explanations on some of these, feel free to ask, right? Because this is something that you're expected to know, but again, since people come from very different backgrounds, you may not have learned this or you may not be familiar with this. So feel free to ask in that case, and we can go over it in the next session. Okay, you would like some explanation. Sure, we can do that. So I'll try to briefly cover the idea of caching with the, I think, direct mapping, set associative mapping, and fully associative. Those are broadly the 3 strategies and what these fields mean in each case. Okay. Let's move on to the next one. Okay. So yeah, this answer was again 21, as most of you guessed correctly. So again, the total number of address bits was given as 32, And so a very easy way of getting the number of bits for the tag field is to take the total number of bits and subtract the sum of both the others. So we already calculated the 5 and the 6 part of it. So you subtract 11 from 32 to get 21. So the total number of bits in the tag field would be 21. Any doubts on this? Okay, if not, let's move ahead. Yeah, so this gets into pipelining and cycle time and latency. So again, data will be common for questions 4 to 8. A non-pipeline processor was redesigned as a 5-stage pipeline processor. The different stages have different latencies. Fetch, decode, execute, memory, write back stages have latencies of 400, 600, 500, 800 and 200 picoseconds respectively. Each pipeline stage incurs an extra 20 picosecond latency on account of the registers between pipeline stages. What is the cycle time of an instruction for the non-pipeline processor? Your options are 1850, 2000, 2500 and 3000. Again, you can take some time to read this and work it out, and then we'll discuss the answer. Okay, 2500. 2500. Anybody else? Anybody who finds this question difficult? Okay, no other answers. 2500. I see very few answers. Do most people find this difficult to calculate? Or you have no idea what's being asked? Okay, let's do a detailed explanation and come back to that question. Okay, 2500 mistakenly included the pipeline latency. Okay. Okay, let's discuss this in detail and come back to the answer. So let's start with pipelining, right? Again, some of you might not have had a computer architecture overview. So this is one of the most frequent questions I get. So I talk a little bit about pipelining here. And the reference, whenever I use a reference that is not there in your slides, I give it as a hyperlink in the slide credits, so you can go look at that source if you want more details on this. And again, these are typically examples that are meant to simplify the concepts for you. So here we have a laundry example for pipelining, right? So we have 4 people, each with a load of clothes, and the processes involved in laundry are washing, drying and folding. The washer takes 30 minutes, the dryer takes 40 minutes and the folding or the folder takes 20 minutes. So for one load of laundry, it takes 30 plus 40 plus 20, 90 minutes, right? This part is very simple. So we haven't gone into pipelining at all yet. So if we did it sequentially, So remember that there are 4 loads of laundry, right? So if you do it sequentially, it will be 90 minutes per load because of the 3 steps that are involved, and it basically takes you 6 hours. So if you start from 6 p.m., you finish at midnight. Now comes the concept of pipelining, right? So what you do while the laundry load A, or the person who had the load A, once it finishes the washer is essentially idle, right? So there is no need to wait till the third step to start load B. Load B can start after 30 minutes itself because the washer is now idle, right? And similarly, once this part, the drying, is done for load A, load B can go into drying. And similarly, even if there is one person folding clothes, once the clothes for person A are done, the folding can start here, right? So this is the idea of pipelining. So now you'll notice, if you actually sit and work this out, and if you've never heard of pipelining before, or if you've not had a Compar course, I would definitely recommend taking this example and drawing this diagram yourself. Okay, I think I just had a network issue and dropped off. Sorry about that. Let me share screen again. Okay, hope you can again hear me. Sorry, I was muted, I didn't notice. Think I had a network issue. Sorry about that. So hope you can hear me and see my screen still. So let's continue with this example, and if you lose me in between, let me know. I did a network check before joining, but looks like my network is acting up today. So anyway, so here's the idea of pipeline laundry. Great, glad you can hear me. So if you've never heard of pipelining before, I definitely recommend working out this example, right? And you'll see that in this sequence, your pipeline laundry takes 3.5 hours for the same 4 loads rather than 6 hours. So you clearly see the benefit of pipelining. So going back to the motivation, can you use idle hardware? In this example, your idle hardware was in the sequential example, your washer and dryer were the idle hardware, and so also the folder, or the person who's folding clothes, because in all these steps the folder is not doing anything, and similarly in this time frame the washer is not doing anything, and so on, right? So the idea of pipelining is, can we use this idle hardware to improve concurrency, to do more work basically. So if you have more concurrency, you can have higher instruction throughput, or how much work you do in one cycle. So the broad idea is, when an instruction is using some resources in its processing, process other instructions using idle resources. So in this example, when your load A was using the dryer, load B can be processed using the washer, right? So you're using other resources that are idle. So similarly, going back to your 5-stage instruction pipeline, when one instruction is being decoded, you can fetch the next instruction. Similarly, when one instruction is being executed, you can decode another instruction. And when an instruction is accessing data or memory, you can execute the next instruction. And when an instruction is writing its results into the register file, access data for the next instruction. So this is the idea of pipelining, and I think there's a diagram. Yes, this definitely helps you understand better, right? So your instruction 1 goes like this. In the first clock cycle, it goes through fetch, then decode, then execute, then memory, and then write back. And while this first instruction is in the decode stage, you start the fetch of the second instruction, or the I+1th instruction. So this is how pipelining looks. So if you notice, so in these stages, right, these are where your pipeline is not yet full. You see all these gaps or bubbles. They are typically called stalls, or this is basically before the pipeline reaches its steady state. But once it reaches its steady state, you'll notice that in every clock cycle there is one instruction completing. For instance, in clock 5, instruction I completes. In clock 6, I plus 1 completes. In clock 7, I plus 2 completes. Clock 8, I plus 3. Clock 9, I plus 4, right? So this continues, and here, although you see empty things, typically the other instructions would come in. So you'd never have empty slots like this. So this is basically improving throughput, or improving how many instructions are completed in every clock cycle. So if you did it sequentially, you would only see completion at every fifth clock cycle. But now you are seeing completion at every clock cycle, and you're utilizing your hardware better. So this is the idea behind pipelining. Is this clear, or are there still doubts about the idea of pipelining? Clear. Okay, great. So now, yeah, and then this is the theoretical idea, but there could be some hazards or something that prevents you from doing this, as in prevents the next instruction from being processed. So one thing is you could have a resource conflict where two things are using the same unit. You could have a data hazard where an instruction depends on the results of the previous instruction. You could also have a control hazard where you have things like branches or stuff that changes the PC, right? So some of these examples were, I think, explained in the week 1 slides. So you can look at that as well. And these can cause pipeline stalls, or basically those empty spots that I showed you. And obviously having a stall in the pipeline will reduce the pipeline performance. Now let's come back to this question. So here we were asked about the cycle time for the non-pipeline processor. So there was data in the question about pipelining. So whenever you see questions like this, right, which have data that are for multiple questions, common data, pay attention to what data you need to solve just this question. So read this question carefully. So here it clearly says non-pipeline processor cycle time. So ignore all information that you have about pipelining for this question. That will help you quickly solve it without getting distracted by lots of data. So in long questions, typically that's the problem. You get overwhelmed by too much data. So pay attention to what you need to solve this question. So here there is no pipelining. So the cycle time has to allow an instruction to go through all the stages in each cycle. So the cycle time is kind of the reciprocal of the clock frequency. So the idea is that one instruction has to finish all stages in this cycle time. So the stage times were given in the question itself. So all you have to do is add them up, add the 5 stage times, which comes to 2500. So this cycle time of an instruction would be 2500 picoseconds. Is this clear now? Any doubts, any questions? Okay, clear. Difference between cycle time and latency, we will get to that. We have questions on that, so I'll wait to answer that in that context. Okay, so yeah. So the next question is this: what is the latency of an instruction, again for the non-pipeline processor? And your options are 2000, 2500, 520, 3500. 2500, 2500. Okay, wait for a few more seconds. Anyone else? Okay. Time until, so what we'll do is we have 2 3 questions on this cycle time and latency. So we look at them in the context of both a non-pipeline and a pipeline processor, and then kind of conclude on what's the difference, right? That will help you really understand the difference completely. But yeah, we will talk about latency in detail. So let's look at the answer for this question. So it is 2500 itself, like many of you said. So for a non-pipeline processor, the latency and the cycle time are the same. So, but in understanding why that is, let's look at the definition of latency, right? So again, I'm putting two ideas here, because with pipelining, we also said that the throughput has to increase, right? The idea is that you get higher instruction throughput. And now you're looking at the term latency. So some of you from a non-CS background might not have heard of these two, and it might be very confusing. So let's look at this. So this is again very generic terms, could be applied to a number of things. So latency is the time, or you can simply think of it as the execution time, or the time to finish a fixed task. So in this case, like someone said, time till another instruction can start being processed, or more specifically, time to finish a particular instruction is the latency. Throughput is typically, throughput or even bandwidth refers to the number of tasks you can accomplish in a fixed time. In this case, it would be the number of instructions processed or executed in a particular time. So these are very different, right? So when you exploit parallelism, your throughput improves, not latency. This is a very key idea to notice in pipelining, and if you don't pay attention, you might miss it. So like I said, here you see that at every clock cycle, one new instruction completes. But if I ask you what is the latency of an instruction, it is still going to be 5 clocks, right? This instruction takes 5, this starts at 2, finishes at 7, or finishes at the end of 6, and so on. So each of these instructions still take the same 5 clock cycles. So by doing a pipelining, you are not changing the instruction latency. What you are changing is the instruction throughput. How many instructions you are able to complete in, let's say, 1 unit of time. That's what changes here. So that's a very key difference between latency and throughput. But again, these may be contradictory, right? You may see examples where throughput is high but not latency. So let's also look at a more simplistic example of latency and throughput, right? So let's take an example of a car and a bus, right? And in this case, your task is to move people for 10 miles. So a car can seat 5 people, or its capacity is 5 people, and its speed is 60 miles an hour. A bus can seat 60 people, but the speed of the bus is 20 miles per hour. Now, if we compare these two on the basis of latency for this task, so the task is to move people 10 miles, right? The car, 1 second, people are joining. Yeah. So you want to move 10 miles and the speed of the car is 60 miles per hour, or 60 miles in 60 minutes. So 10 miles takes you 10 minutes, right? On the other hand, the bus speed is 20 miles in 60 hours. So if you have to move 10 miles, it takes you 30 minutes. So you can see that on the side of the latency, lower is better for latency, right? Basically, it's execution time. So faster the better. So the car is faster. The car is better on latency. Now let's look at throughput, right? How many people per hour can you transport? So given that the task is moving people 10 miles, and notice that you're counting the return trip. So you in an hour, so here the unit of time is hour. So in an hour you can move 15 people. Why is it 15? In 10 minutes you can move 10 miles, come back with the same, let's say, 5 people. So that's 20 minutes for 5 people. So in an hour you can do 3 such trips, which is 15 people, because at a time you can transport 5 people. Now the bus takes 30 minutes, so it can only do 1 round trip, going and coming back. But remember that it seats 60 people, right? So the bus can transport 60 people per hour. So now look at this. So throughput higher is better. This is always something you should ask yourself. Whenever you see a metric, think of is it better if it's lower or is it better if it's higher? So in case of latency, lower is better. So remember, see that the one that has the lower latency is in bold. Whereas for throughput, higher is better. How many instructions do you want completed per, let's say, minute? Higher is better, right? Similarly, here the bus has 60 as opposed to 15. Therefore, the bus is better on throughput. So you can see a contradictory example here where car is better on latency and bus is better on throughput. So these two ideas are something that's very key and that will help you throughout multiple topics in systems. You can also go through this later if you want, and I've also left the link to where I picked this from, so you can take a look at that. But this is the idea behind latency and throughput. So for people who asked about the definition of latency and maybe people who had doubts on throughput, does this help, and or do you still have doubts? With respect to cycle time, we'll address that after the pipeline question also. But is the idea of latency and throughput clear? Are latency and throughputs trade-offs in instructions? So voice is breaking. Okay, let me just pause for a few seconds, see if it gets better. Is it any better? Can someone confirm if you can hear me clearly? Okay, great. So are latency and throughput trade-offs in instructions? So they need not be, right? But when you do pipelining, that's essentially you're not really trading off latency to get throughput, but you are increasing throughput while not really affecting latency. So if you go back to our laundry example, right, you can see that the latency was for a particular load, it was 90 minutes. It still remains 90 minutes. So you're not affecting the latency, but you're improving the throughput by doing pipelining. But are there other methods where there could be trade-offs? Depends, right? So it need not always be a trade-off. I'm not saying that latency and throughput are always trade-offs, but they can be trade-offs. So don't assume that improving latency improves throughput or vice versa. That's all I'm trying to say. Okay, I'm hoping this was helpful. So let's go back to our question. So with the same data, what is the cycle time of an instruction for the pipeline processor? Again, take 2 minutes to solve this. Since it's been a while since you looked at the question, let me go back to the question. Yeah, here's the question. 820, okay. Think about this for a little bit. What is the cycle time for the pipeline processors? $820 picoseconds, okay. $820, okay. Okay, let's take a look at the answer. So let me go all the way down. we did this. We're looking at cycle time for a pipeline processor. It is 820, right? So here the idea itself is different. So in a non-pipeline processor, you basically want to set your cycle time or your clock, right? This is basically about clocking. So you treat the entire instruction as one indivisible thing, right? And whatever is the time that it takes for the instruction to execute, your cycle time becomes equal to that, or your clock is set in such a way. But when it's pipelined, think of splitting up the same instruction. Maybe it's not longer, right? We are just splitting it into multiple stages, right? And now you want to clock it. You want to treat each of these stages as an individual element depending on which you want to clock it. So remember, when we talk about instructions as a single element, right, we have to set the cycle time or the clock to account for all stages. So some instructions may not go through all stages. For example, they may skip a particular stage, but since you are kind of setting the clock, you have to account for the worst case, or the case in which all 5 stages are there. So here the logic is similar, but instead of setting the cycle time as the sum of all 5, you look for the critical path or the longest stage, the thing that's going to be your bottleneck, and that becomes like your common factor. So here if you look at your stages, they are 400, 600, 500, 800, 200, and additionally you have a register delay at the end of each stage. So you pick the maximum out of this, which is 800, add the register delay, that is going to be 820. So in a sense, you're saying that regardless of how much time this particular stage is going to take, I'm going to set a common denominator of 820 for all of them. That's what the cycle time indicates in the pipelined case. So now is this clear, or are there any further doubts on what is cycle time? So the notion is slightly different in a pipeline and a non-pipeline scenario. Clear, great. After fetch 400, it will go for decode. Yes, so cycle time is not the time it's going to take for the instruction to complete. This is kind of the time at which your clock is going to change, right? So it's like a common denominator. Earlier it was the full instruction time. Now you want to do this after every stage, but you cannot pick 400 because there are some things that are greater than that. So you have to pick the largest one, which then will account for all of these, right? That's kind of what we use for deciding the cycle time. So think of it this way, right? If you have to, if there are 3 things that are operating at a different speed, and if you have to wait for all 3, then you are going to be bottlenecked by the slower one. So if you have to set a deadline, you will set a deadline based on the slowest one, or the thing that's going to take the maximum time. It's the same idea here. So the cycle time is not indicative of when the instruction will complete. So within 800, fetch and decode will be done. No, that's not at all the idea. So this cycle time is just for within 800 fetch and decode. Okay, if you interpret it as 800 absolute units, yes, everything else will be done within 800, right? So that's kind of the idea. That's why you pick 800. So I initially said no, assuming that you're talking about 0 and then 400 and then 600 for the next stage. So fetch and decode will not be done within 800 picoseconds because they're going to take 400 plus 600. But no, just to clarify, I'm talking about 800 as the maximum because every other stage will be done within that time. So 800 is your bottlenecking stage, or the stage that's going to take the longest time. Hope that's clear. Memory access takes more time. In this case, yes. We are finding CP of an instruction for a single stage, that is fetch. I don't really understand that comment. Is that a question? We are finding cycle time to be to accommodate for all the stages and the fact that each of those can take different amounts of time. So we are basically setting it in such a way that all of these stages can execute within that cycle time. That's the idea. Yeah. Okay, we will move on in the interest of time. Okay. What is the latency of an instruction for the pipeline processor? So in solving this, try to go back to the definition of latency that we discussed and then give me an answer. $4,100. Okay. Okay, this seems a bit confusing for everyone, or you guys are taking time to compute. That's fine. Take your time. I'll give you another 2 minutes. $4,100. Okay. $2,520. Okay. Anyone else? Okay, let's take a look at the answer. It is 4100. So how you get this is 5 into 820. So this, I understand, might be a bit confusing, right? Because you're giving the individual stage times. So your instinct is to add up all of these and say that this is what it takes. But remember that I said this was about clocking, right? And the idea of setting the clock is such that when the clock or the cycle elapses, the data flows, right? So this stage may finish in 400 picoseconds, but because we set the cycle time to 820, it's kind of going to the next stage only after 820. This is something we are forcing for the sake of uniformity. This is basically the notion of clocking, right? How you decide your clock frequency or your cycle time. Since we picked it to be 820, we are essentially saying that regardless of what times these individual stages are going to take, we are going to clock it such that each cycle finishes or goes to the next stage at 820 picoseconds. So then your latency simply becomes 820 into 5 for each stage, which becomes 4100. And this number already takes into account the register delay and things like that. So it is 4100. Any questions on this? I'll give you a minute. Okay, what is the difference between pipelining and instruction level parallelism? Yeah, that's a good question, but in the interest of time, maybe I'll take that up in the first part of the next live session, because I think we have 2 more questions to go through. Will stalls in the pipeline, because that's a slightly different topic that we have not really touched upon, so we will come to that. Will stalls in the pipeline cause latency to increase? Yes, definitely. But here we are not really talking about stalls in the pipeline in a sense. A stall is when a stage has nothing. Here we are talking about kind of clocking it to, in this question, right, kind of setting the cycle time such that all stages can finish within that clock or within that cycle time. But typically, if you have stalls in the pipeline, let's say you had an if condition and you didn't know which branch it was going to take. So your branch predictor predicted something and you may have fetched that instruction, but the actual branch it took was wrong, which you find out only much later, and then you flush the pipeline. So this causes an increase in latency. You could also have a stall due to some resource conflict or something like that. Typically, all of that definitely will cause an increase in latency. Okay, moving to the next question. A CPI of 10 was observed from simulation experiments conducted with a perfect cache for a processor with clock rate 5 GHz. A 64 KB L1 cache having miss rate is 4% and cache miss penalty is 60 nanoseconds. What would be the CPI with the 64 KB L1 cache? 5, 8, 10, 12. By the way, for this question, I think the options given in the answer key are incorrect. So feel free to calculate this, and if the options don't fall in any of these, you can tell me your answer. I think I looked at it, but I didn't have a chance to correct it. Any answers? This also probably was not covered directly in the lectures, so it's fine if you don't know. CPI full form, cycles per instruction. Okay, if nobody has an idea, let's look at the answer in the interest of time. So the answer is 22. So I think this needs to be changed to 22. I'll do that before uploading the slides. But let's look at how you come up with this, right? So the clock rate is 5 gigahertz. So the period or the reciprocal of the frequency 1 by 5 gigahertz comes to 0.2 nanoseconds. Now you're told that if you undergo a cache miss, the penalty or the time it takes is 60 nanoseconds. So if again you convert this into cycles per instruction, you get 300, right? Now the CPI that you get, the CPI that was already given to you is an ideal one, basically assuming 100% cache hit rate. But you are asked about the CPI for this particular cache which has a miss rate of 4%. So how you calculate that is take the observed or the ideal CPI plus the penalty that you incur for the cache miss in terms of CPI. So the ideal CPI is 10 and 4% of the time you're going to get a cache miss because that's the miss rate given to you, and that becomes into 300. Shouldn't it be 0.96 into 10 plus 0.04? Let me think about that. I think I remember that there was a mistake in this question. So what does 0.96 into 10 plus that give you 9.6 plus 21.6. Okay, let me think about that and then come back to this question, because I think there was a mistake in the options anyway, and I'm not sure if this is correct. So let me check and I'll get back to you on that. Okay, 21.6. But this is the overall idea. So you take the CPI that you are given and you account for the cash miss penalty, and then you add both of those and come up with the overall CPI. Okay, 10 into 0.96 plus 310 into 0.04. Okay, I will verify this. Thanks for pointing that out. I will verify this and get back to you. Okay, so we are almost at the end of the session. So let's use the last 1 minute. I think I had 2 more questions which I'll just add to the next session. So we'll anyway go through that. But if you have any other doubts or questions or any comments on how you found the live session or how you want the next one to be, please use this 1 minute to post it on chat. If not, you have nothing else to say. Thank you so much for joining and keeping it interactive, and look forward to seeing you next week as well. I don't have an NVIDIA GPU. How do I run CUDA code? I don't know if this course gives you access to do something like that. Collab and things like that might also give you some free accounts with your academic credentials, but I don't have the details for that. I can check and get back to you. You can also do a quick check on that. If typically platforms give you some free credits or some access to some GPUs, so you can look for that. Yeah, you're very welcome. See you next week. If you have any doubts, please post it on chat. I'll stay around for another minute. You're welcome. Glad you found it useful. Thank you. Okay, if there are no questions, thank you so much and see you next week.